Hi everybody, welcome to another video in Trigonometry, section 5.2, Sum and Difference Identities. So as far as identities, trigonometry identity goes, this is the most difficult to prove. In fact, I'm going to skip the proof. If it is the regular lecture class, I actually will spend time to prove some of this. But since it's a video, I try to keep it short. Right, so the identities. Most of the other identities in this chapter will be derived from this. So this will be very fundamental, difficult to prove. Once we know this, we can prove a lot others trigonometric identities. So let's look at these identities. Pay attention on cosine and sine first. So cosine of a sum, cosine of a difference. What we see here is that for cosine, sum or difference, we have the cosine, sine and sine. So the products of the same function, right? Cosine, sine, sine. But the sign in the middle are opposite. So the way I memorize this is that for cosine, we have product of same function. I mean cosine go with cosine. And the sine in the middle, opposite middle sine. Yeah. If that's a plus, that minus. If that minus, that a plus. For sine, we have sine, cosine, sine. So it's going to be product of different function. So different function in the product. But the sign in the middle are the same. If it is plus, that's a plus. If it is minus, it's a minus. And one thing that's common to all of them is cosine, we start with cosine. If it's sine, we start with sine. And of course the tangent, it's going to be that. I have no trick for that. Right, now, like I said, if we have to actually prove some of this, it will be at least 15 minutes to prove one of those. So I'm not going to spend time on that. Right, now, the rest of the section is just the application for these identities. So first, we can use this identity to prove the CoFunction identities. So CoFunction identities, as mentioned before, I think this is in chapter 1, CoFunction identity. Sine of anything is equal to the CoFunction, sine, cosine. And if we want to go from the function to CoFunction, the angle is going to be complementary, meaning subtract from 90 degrees. Here I have pi over 2, which is equivalent to it. So if we want to go to a function to a CoFunction, the angles must be complementary, meaning this angle, the angles must add up to 90 degrees. Right, so that goes from function to CoFunction. The angle go to complementary of that angle. Right, but if we want to prove something like this, let's start with the more complicated sine. Now, according to that identity, sine will be a different function in product. So meaning we're going to have sine. So then we start with sine, cosine. The sine in the middle will be the same, and then cosine, sine. Yeah. And then the angle pi over 2 x, pi over 2, and x. Next, sine pi over 2 or sine of 90 degrees is going to be 1, and cosine of 90 degrees is 0. 0 times anything is 0. So we just have 1 times cosine, which is cosine. Which is good. And that is the right hand side. So just that's the proof. Simple enough. Now the next one is not as simple as it looks. I'll write it out first. The problem with this is if we have tangent of pi over 2 minus x, tangent is tangent pi over 2 minus tangent of x over the product 1 tangent. Right, so will be that. I've just copied that identities here. Right. Now the problem with this is tangent of pi over 2 is sine of pi over 2. Tangent is sine over cosine. And sine pi over 2 is 1. Cosine pi over 2 is 0. And so tangent of pi over 2 is undefined. So because this is undefined, we cannot use this identity. Well, that doesn't work. So that's why this identity, we're not going to use this. What we use is something similar to it. Once again, start from left hand side, which is more complicated. But we cannot use this. Now if we cannot use that, what can we use? What else can we use? Of course, the more fundamental tangent is sine over cosine. Because when we write everything in terms sine cosine will be defined everywhere. So we don't have to worry about when it is undefined. Right. And then so we just write for both of them. For sine, it's going to be the same. I mean, different function in the product. Sine, cosine. But the sign in the middle is the same. If it's minus, it will be minus. Then cosine and sine. Cosine will be the same function in the product. But the sign in the middle are opposite. So sine of pi over 2, that sine of 90 degrees is 1. Cosine pi over 2, cosine of pi over 2, cosine of 90 degrees is 0. Right. While we simplify everything, what's left? So the 0, that gone. 1 times cosine, so we have cosine on the top and sine at the bottom. That gives us cotangent of x. So, simple enough. So that certainly works. This will not work because tangent of pi over 2 is undefined. Right. So that's nice, you know. That's certainly nice. Right. Remember, we have the next we find exact values of this. The problem with this is we have the exact values of 30, 45, and 60 degrees. Right? Or multiple of those. Equivalently, pi over 6, pi over 4, and pi over 3. This is neither. Right, so somehow we have to simplify this. I mean, not simplify. Somehow we have to write this as something we know. And that something we know is 75. How about 30 plus 45, right? We know exact values for 30. We know exact values for 45. So that certainly works. So instead of write the exact value for that, we try to write everything as a combination of 30, 45, and 60. Or equivalently, pi over 6, pi over 4, pi over 3. Maybe pi over 2 too, if we need to. Right. So again, sine will be different function in the product. sine, cosine, plus cosine, sine. It's been a while. Still have it. Sine of 30 degrees. Sine of 30 degrees. Sine is finger on the right, so we have square root of 1 over 2. Cosine 45 degrees. Cosine number finger on the left, square root of that, divided by 2. Cosine 30 degrees. Cosine number fingers on the left, square of that, divided by 2. And sine 45 degrees, finger on the right, square of 2 over 2. Right. And then we simplify that. Multiply straight across, square root of 2 over 4 plus square root of 6 over 4, and we can bring both of them under one fraction. Square of 2, square of 6. Simple enough. Right. Next, 105. How do we write the combination? How do we get 105? So that could be 180 minus 75. We know 75 now. Or we could go like 135 minus 30. 135 are multiple of 45, which is still good. Or we can say 30 plus 75, but it's not going to help because we only know sine. Yeah, we can find cosine of 75, but because the more direct way is 60 and 45, right? Or you can go 135 minus 30. That certainly works. Right. Cosine of a sum. Cosine product of same function. Subtract. Right, now we just find the values. Cosine 45 degrees, square of 2 over 2. Cosine 60 degrees, 1/2. Sine 45 degrees, square of 2 over 2. Sine of 60 degrees, square of 3 over 2. Right, so put them together, multiply straight across, square of 2 over 6. I don't know why I get 6. Multiply this, square of 6 over 4, and combine like terms. Square of 2 minus square of 6 over 4. And square of 2 less than square of 6, so the answer here is negative. And cosine of 105, it is in the second quadrant, so it should be negative. So, let me check. Right, so that's simple enough. Of course, here we didn't go something less conventional. We might have something, let's say, tangent of pi over 8. Never mind. So that is, yeah, that will have to be in the next section. That's not what I mean. Pi over 12, that's what I mean. Pi over 12. Right, how do we get pi over 12? So it's always more difficult if we work in radian, we don't get idea. But if we convert this to degree, maybe it help. Convert to degree, put degree on top, pi at the bottom. Cancel out. 180 divided by 12 is 15, so that is 15 degrees. And 15 degrees, of course, we can draw a tangent of 45 minus 30. And we can use this identity and go from there. But the idea is trying to write, if you want the exact value, trying to write a combination of 30, 45, and 60, or multiple of those. So if we have like something a lot bigger, like instead of 165 degrees, for example, what is sine of 165? Then of course 30, 45, and 60 don't add up to that, but we can also use 120 and 45. So 120 is of course multiple of 30 or 60. So that certainly works as well. So with that, we can write the trig values for a lot of other values. Of course, pi over 8, that will be in the next section. Right, next. Given sine of u equal to negative 3 over 5 and u in the third quadrant, cosine v is 12 over 13 in the fourth quadrant. Find sine of u plus v. Right, let's start with sine of u plus v is what? Sine of u plus v is equal to sine and cosine, different function with the same sign in the middle. Cosine, sine. Right, so what do we have here? Sine u is negative 3/5, so we know this. So that's one's good. We know cosine of v as well, so this is also good. Cosine of u, we don't know that. And sine of v, we don't know that either. But we can find it. We can find them certainly. Right, so just need to find cosine of u and sine of v, put it back in here, and that will work, right? Right, so now let's work on this one first. Try to find u. So we have that. And of course what we need is cosine of u. So of course there are a lot of different ways to do this. But of course Pythagorean identity, sine square plus cosine square equal to 1. We certainly can solve for cosine square and then solve for cosine. Right, I do it differently. The most fundamental way when we do trigonometry is to go back to the definition. Sine is y over r, right? So with this, r is always positive, so r is going to be 5, so y is negative 3. And with that, we can just solve for x. X squared plus y squared equal to r squared. So y squared is negative 3 square, r is 5. So we have 5 square and 3 square move to the other side. 25 minus 9, that is 16. And take the square root on both sides. Remember, when we take the square root on both sides, it should be a plus or minus. So in this case, we have x is plus or minus 4. So is that a plus or is that a minus? Well, easy to determine that because it is in quadrant 3. In quadrant 3, it's going to be negative. So x is negative 4. So in that case, we go back and we try to find cosine of u. It's going to be x over r, negative 4 over 5. Of course, we did plenty of this in chapter 1. So that's negative 4/5. That's first. Now we take care of cosine of u. Now same thing, we'll find cosine of v based on the information we know about v. Cosine of v is 12 over 13. And v in quadrant 4. Cosine of v is x over r equal to 12 over 13. Once again, r is always positive, so we know for sure r is 13. And in that case, x must be 12. So again, Pythagorean identity, x squared plus y squared equal to r squared. This is Pythagorean theorem. Right, so r is 13, x is 12 squared. So for that, and so we have y squared is 13 squared minus 12 squared, so that will be 25. And check the square root on both sides. So if y equal to plus or minus square root of 25 was 5. And next, this is in quadrant 4. In quadrant 4, y is negative. So we need to find sine v, right? Sine is y over r, so negative 5 over 13. That's what we have. And now we'll go back to our problem. Sine of u is negative 3 over 5. Cosine of v, 12 over 13. Cosine of u, found that, negative 4/5. And sine v, negative 5 over 13. Right. At the bottom, there's 5 times 13, which is 65. On the top, we have negative 36. And negative, not plus 20. So the answer is negative 16 over 65. Next, go to this problem. So we start with cosine of u plus v. So be cosine minus sine. Right, what do we have? We know sine of u and cosine of v. We don't know cosine, and we don't know sine v. Cosine u and sine v. That's perfectly fine. We do the same thing as we did before, and we can find those values. Alright. Now let's look at this one first. And this is in quadrant 2. So sine of u is 7 over 25, and u is in quadrant 2. Sine is y over r is equal to 7 over 25. So in that case, r is equal to 25 and y is equal to 7. Right? Pythagorean theorem, Pythagorean identity. Actually, this is Pythagorean theorem because we do have a right triangle. Right. Put in 25 for r and then 7 for y. So x squared plus 7 squared equal to 25 squared. Right. Now just solve for x. (25 square) minus 7 square, square root of that, 24. Again, don't forget there's plus or minus when you take the square root on both sides. Right, and this is in quadrant 2. In quadrant 2, x is negative. So x is equal to negative 24. And we have sine of u. We need to find cosine of u. So in that case, cosine of u is x over r, negative 24 over 25. So now we take care of that. Now we go to v. To go to v, we solve for sine of v. So cosine of v, x over r. Again, r always positive, so that's why we can just say x is going to be negative 5. So r is 13 and x is negative 5. Right? And then of course Pythagorean theorem, negative 5 squared, so y squared, 13 squared minus 5 squared. I think we did that earlier. That could be 12 squared, 5, 12, and 13. Anyway, so it's be 144 if you do the math. And then so y equal to plus or minus square root of 144 plus or minus 12. Now in quadrant 2, y is positive. So y is positive 12. And so for v, just need to find sine of v, and sine is y over r. So this is 12 over 25. I don't know why they have 25, not this, but y over r, 12 over 13. And finally, we go to put all the numbers we know. Cosine is given. Cosine of u, actually we found that, negative 24 over 25. So, cosine of u, cosine v, that is given negative 5 over 13 minus sine of u, that check mark, so that's given 7 over 25. And then sine of v, 12 over 13. Right. Now at the bottom we have 25 times 13, that is a common denominator. 20 and 25. And then negative 24 times 5, 24 times 5, that will be 120. Negative times negative is positive. 7 times 12, 84. So the answer is 25. And 120 minus 84, so that's 36. Right. So that's what we have. Now, so we have both of u and v in quadrant 2. So when we have two numbers in quadrant 2 add together, this could be in quadrant 3. So if we have a numbers in quadrant 2, which means between 90 and 180, both of them. So when we add them, so u plus v is between 180 and 360. So the answer could be in quadrant 3 or quadrant 4. So when we do this, it turned out to be positive. So we know that the answer u and v should be in quadrant 4. Right. So that's all we have here. So we just need to do a bunch of practice. It's straightforward, those identities. And that's what we have in this section. Once again, I will stop the video here. As always, thank you for watching and see you in another video in trigonometry.